always. Last week we studied subspace of vector space. The vectors we know already what it is. That is something with two operations satisfying 10 property, 10 axioms. In Vietnamese, 10 tiền đề. So now we consider a subset W of V. If W together with the same operation of V is again a vector space, then W will become a subspace of V. I'm sorry, let me see what we can do. Okay. That is a definition of a subspace. However, the below of the screen you are seeing here, then use that usually to verify if something to be a vector space, you need to verify 10 property, 10 axioms. But however, to verify a subset to be a subspace, you need to verify only two things. That is property number 1 and property number 6 in the definition of vector space. That is what is written in the screen here. That appear already in your exercise. So I repeat it here for you. And I show you some examples from already from high school. For space, for the plane, I mean the coordinate plane, mặt phẳng tọa độ. Any straight line going through the origin will be a subspace of the R2, the 2 space. And any other straight line not going through the origin cannot be a subspace. And for the case of 3 space, you see any line going through the origin and any plane going through the origin will be the subspace of R3. Bất kỳ một đường thẳng nào đi qua góc tọa độ, bất kỳ một mặt phẳng đi qua góc tọa độ đều là không gian con của không gian 3 chiều. And we know that suppose that V and W are both of them are subspace. Both of them are subspace of a vector space U. Then the intersection of them will be again a subspace of U. But you should remember that the union is not a subspace. You can find a counter example in the geometry, and during the exercise using the tutor class you can ask your teacher. And next we study what we call spanning set and linear independence. Suppose that we are given a set S of k vector inside V. Then span of S will be the set of all linear combination of vectors inside S, or by formula you have span of S to be that one. Here Ci is any number, any real number. And another notion is a spanning set of a vector space. I say that if any vector in the vector space V can always be written as a linear combination of vector inside S, then S will become a spanning set of the vector space V. Or you can say V equal span S, because span S is that, and any V, any element inside V can be written as an element of vector in S, means we have a span of S equal V. And in Vietnamese we have two notion. Span S là cái tập sinh bởi S, còn span spanning set của một không gian vector, spanning set of a vector là tập sinh của một không gian vector. Hai khái niệm khác nhau, các bạn phải cảnh giác về cái đấy, không có là lẫn. Next, the example here show you that any exercise concerning a spanning set or span of S is always related to the system of linear equation. And here, the exercise requires you to verify that the set S of three vectors like that is a spanning set of R3. How you can do it? You need to show that for any vector U with three coordinates U1, U2, U3, that equation is consistent, means it always has solution. And we write it now in the form of a system of linear equation like that. So you need to show that system of linear equation has solution for any right-hand side U1, U2, U3. And you know how you can do it. You can apply Gauss-Jordan elimination to solve it. You can apply the Cramer's rule to show that the system has unique solution or something like that. I only want to tell you that any exercise concerning spanning set is always reduced to the system of linear equation. Here is some property for span of S. Span of S, we say in Vietnamese là tập sinh bởi S. But however, the first property saying that span S is always a subspace of V. So we can say in Vietnamese, span S, in Vietnamese you can say không gian sinh bởi S, because it is always a subspace of V. The next property saying that every subspace of V which contains S must contains also span S. It means that span S is the smallest subspace of V which contains S. Span S là cái không gian con nhỏ nhất của V mà chứa S. And then we go to the notion of linearly independent and linearly dependent. Suppose that we consider the set of k vector v1, v2, vk like that, and we consider one equation c1 v1 plus c2 v2 plus ck vk equal 0. And 0 here is a zero vector because v1, v2, vk are vector inside V. So we consider that equation, and here in the equation the unknown is a c1, c2, ck, and we need to solve that. Mean to solve the equation means we need to find c1, c2, ck, and it is easy to see that the equation always has the trivial solution c1 equals c2 equals ck equals 0. Then the set S will be called linearly independent if the equation has only trivial solution, means it does not have any other solution. But if the equation has non-trivial solution, it means that it has a solution where at least one CI is non-zero. Then the set S will be called linearly dependent. Linearly independent là độc lập tuyến tính. Linearly dependent là phụ thuộc tuyến tính. That is in Vietnamese terminology. And the first property about linearly dependent is following. If we consider the set of k vector which k is more than 1, it means at least 2 vectors, then S is linearly dependent if and only if at least one vector Vj inside S can be written as a linear combination of the other vectors inside S. I will not explain it here more, but Now I want to consider only one special case. That is the case when the set S has only two vectors U and V. In that case, the set U and V will be linearly dependent if and only if U equal k time of V for some number k. And if you can imagine it, you can look it at the vector like what you know already in the high school. Then U equal kv, that is something like that. U can be the blue arrow and V is the purple arrow, like that. It means that two vectors are linearly dependent if and only if they lie on the same straight line. Hai vector là phụ thuộc tuyến tính, hai vector trong hình học là phụ thuộc tuyến tính khi và chỉ khi chúng nằm trên cùng một đường thẳng. Next, we consider the notion of basis and the dimension. The basis is something like that. Suppose that we are given a vector space V, and in that we have a set S of n vector V1 up to Vn. If S satisfies two conditions A and B at the same time, then S will be called a basis for V. So A says that S is a spanning set of V, and the B says that S is a linearly independent. So that is a two requirement for a set to be a basis. The first example is the basis for the zero vector space. The vector space consisting of only one vector will have a basis is empty set. We agree with that by consent. Chúng ta quy ước rằng là cơ sở của cái không gian vector mà chỉ gồm vật từ không là tập rỗng. The next one, that is a standard basis for R3. It has a basis usually denoted by I, J, K. I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. That is a three unit vector in the coordinate space. We have it in the high school, so I will not draw it here. We generalize it, get the standard basis for n space. It consists of E1, E2, En, with E1 like that, E2 like that, and En to be like that. Example, if you consider R4, you get that one. The basis consisting of four vector. A standard basis for the space of all m by n matrices consists of E, I, J, with I runs from 1 to m and J from 1 to n. And because of that, we see the basis consisting of m multiplied by n element. And here is an example with m equal 2 and n equal 2. We get a basis consisting of that. And the last one, that is a standard basis for Pnx. And I will not go into the detail here because that explained already in the last week. Then here are some properties for basis. For a basis, suppose that S equal V1 up to Vn is a basis for a vector space V. Then any vector inside V can be written in one and only one way as a linear combination of vectors inside S. And that property is very important because with that, we will define the notion of coordinate with respect to a basis that we will study by the end of today or maybe next week. Khái niệm tọa độ của một vector tương ứng với một cơ sở là khái niệm chúng ta đã biết từ phổ thông và chúng ta sắp sửa học, hoặc là tuần này, hoặc là cuối buổi hôm nay, hoặc là sang tuần sau. We have one more property about the linear independence and the basis. Suppose that we have already S consisting of n vector v1 up to vn to be a basis for a vector space V. Then any other set of V containing more than n vector must be linearly independent. So it means that you have n vector to be a basis, then any set have more than n vector must be linearly dependent. Phải là phụ thuộc từng tính. And the last one, the last claim of this slide will be useful for the next slide. That is, suppose that a vector space V has one basis consisting of n vector, then any other basis of V will have exactly n vectors. It means that on the basis of a vector space always have the same number of vectors. Then we define the notion of finite dimensional space and infinite dimensional space. I will not repeat it here, but I will go to the notion of dimension because that is very important for the class today. We consider only the case when the vector space V is finite dimensional. Then the dimension of V will be defined to be the number of vectors in a basis. Here, suppose that V is a vector space, S is a basis for V. Then the number of vectors inside S will be denoted by that and will be called the dimension of V, denoted by that one. And we summarize something like that. Suppose that we know that dimension of V equal n already, and S is any subspace of V. Then S is if S is a spanning set or generating set of V, then the number of S must be at least n, means it is greater than or equal n. And if S is a linearly independent set, then the number of S cannot over n, means the number of vector inside S is less than or equal n. And in case S is a basis for V, then the number of S is equal exactly n. And our example in the previous slide shows us the n space Rn has a dimension n. The space of on m by n, which is will has dimension m multiplied by n, because we count the number of vector inside the standard basis here. Similarly, the vector space Pnx has a dimension n plus 1. And the last one, that is the case, the space of Px, that is the space of any polynomial of any degree. That is an infinite dimensional vector space, and we write dimension of Px equal infinite. And finally, we have two criteria to verify if some set to be a basis. I repeat that a set to be a basis if it satisfies two conditions at the same time. But here you have two criteria which it will make you easier in verify something to be a basis. Suppose that we know already that V is of dimension n. Giả sử ta đã biết trước là V có chiều bằng n. Now we consider a set S of n vector V1, V2, Vn. Now you need to verify only one of condition. If S is linearly independent, then S must be a basis. Or if S is a spanning set for V, then again S must be a basis for V. Nếu chúng ta biết chiều của không gian là bằng n, biết rằng tập hợp S có đúng n vector thì chúng ta chỉ cần kiểm tra một trong hai điều kiện. Hoặc là S là độc lập tuyến tính thì nó bắt buộc phải là cơ sở. Hoặc là S là sinh ra toàn bộ không gian V thì S cũng là cơ sở. Chúng ta chỉ cần kiểm tra hai điều đó thôi. So that is all what we studied last week, and now we continue something more. Here is what we know already. That is, we can verify vector some set S to be a basis or not by verify only one of criteria, one of condition in definition of a basis. And today we are going to study more about that. That is, we are going to define what we call four fundamental subgroup of matrix. So before that, I need to give you some notation. Suppose that we are given a matrix A of size m by n, m rows and n column, and we can divide A into rows. So it has m rows, A1, A2, and Am, and we write it as row vectors or row matrix, and it is here. A1 to be the first row, A2 to be the second row, and Am to be the m rows. Similarly, we can define the columns vector of A. Means we divide A into column A1, A2, Am, like that. And it is here. We write it in the column, and it is A1, A2, and Am, like that. Now, we define the following. For m by n matrix A, the row space of A denoted by AS of A, that is a subspace of AN, spanned by rows vector of A, or by formula AS of A is a set of all linear combination of rows vector of A. It is here. Alpha 1, alpha 2 up to alpha m are any real number. That is a row space. And we can do this similar thing for columns. We define the column space of A. Column space of A, that is a subspace of M, spanned by the column vector of A. Means column space of A equals the set of all linear combination of columns vector of A here. And in this formula, beta 1, beta 2 up to beta n are real number. Next, we define one more thing. The next one, we define what we call known space of A. The known space of A, that is a set of all solution of homogeneous system of linear equation AX equals 0. Or by formula, the known space of A denoted by NS of A, that is a set of all X inside Rn, so that A multiplied by X equals 0. And the last, now we have three subspace. The last one is the fourth one, that is something similar to null space. We call it left null space. The left null space of A is exactly the null space of A transpose. Means first we take the transpose of the A and then we consider the homogeneous system of linear equation AT multiplied by Y equals 0. And on solution we make a subspace of AM. We denote it by here NS of AT. And that is the set of on Y in belongs to AM, so that A transpose multiplied by Y equals 0. So far we define already 4 fundamental subspaces. So I show you some notation. On the left hand side here, that is the notation we use in this code at USDH. The first one, row space of A, we denoted by AS of A. The column space of A, we denoted by CS. And the null space of A, we denoted by NSA. It is very easy to imagine. The last one, the left null space of A, we did not use any special notation. We use that the same like a null space. Null space of A transpose, that is the left null space. So we have that one. And on the right hand side, I give you some other notation you can find in other textbook. You can know, you can imagine that different textbook can use different notation, but I require that in this course we use only this notation. Now I go to the notion of the rank of a matrix and the rank of a system of linear equation. Now, before anything, I repeat something you know already, you studied already several weeks ago. But suppose that we are given two matrices A and B of the same size m by n. We say that A and B are row equivalent to each other if the matrix B can be obtained from matrix A by applying a finite number of elementary row operation. Hai matrix A và B được gọi là tương đương hàng với nhau nếu ông matrix B có thể nhận được từ ông matrix A bằng cách áp dụng một số hữu hạn lần các biến đổi sơ cấp về hàm. Then we have a claim. The claim says that if matrix A is row equivalent to the matrix B, then they have the same row space. If A and B are row equivalent, then the row space of A equals to the row space of B. Or in other words, they have the same row space. That one is very important thing. Here I can write it in the formula. Suppose that we denote the small a is any elementary row operation. Then the row space of A and the row space of A mean we apply the row operation on A. They are always equal each other. Means if we apply A into A, row space is unchanged. But however, elementary row operation will change the column space. So that is something you need to remember. You need to be careful in doing your exercise. Now, as I told you, the basis is something important. Sometimes you need to find the basis for a subspace. And we know already row space of a matrix is a subspace, and you are required to find a basis for the row space of a matrix. How you can do it? How you can do it? And here is the way you can find. You can find the row, the dimension, the basis for row space in a very easy way. Suppose that A is row equivalent to B, and B is already in the row echelon form. Then the non-zero row vector of B will form a basis for the row space of A. Means the number of non-zero rows of B will be the dimension for the row space of the matrix A. And here is the example. It's very easy for you to follow. Suppose that we are given a matrix A like that. That is big enough for us. You need to find a basis for row space of A. We do as follows. We apply Gaussian elimination to transform A into B. Obviously, the Gaussian elimination here consists of many operations. So I omit it, but however, in your exercise, you need to write down any details operation you apply. Anyway, now A is row equivalent to B, and B is already in the row echelon form. It has three non-zero rows, W1, W2, and W3. So here I give some notation. The first column of A will be A1, A2, and A3, and the first column of B will be B1, B2, B3. Yeah. Anyway, now if we consider the rows, B has three non-zero rows, W1, W2, and W3. And because of that, the basis of row space of A will be the non-zero row vectors of B, means those vectors are a basis for row space of A. It is here. And there is one thing why in the previous slide I denote the first column by A1, A2, A3, A4. And for B, we denote it by B1, B2, B3, B4. Because if you look at the matrix B, it is very easy for you to verify that equality. B3 equals minus 2 B1 plus B2. And it implies that A3 equals minus 2 A1 plus A2. And more than that, it is easy for you to see that B1, B2, and B4, that is linearly independent. And because of that, you have A1, A2, and A4 is linearly independent. And that is the first observation in this example. Now, we have another example. You need to find a basis for a subspace. And that subspace is spanned by S. It means that we are given a set S of three vectors V1, V2, V3 with coordinate like that. Now we know already that span S is a subspace of S3, and we need to find the basis for that subspace. How we can do it? We write A to be a matrix like that. The first row is V1, the second row is V2, and the last row is V3. So we know that span S is a set of all linear combination of V1, V2, V3. And it is exactly the row space of A. So now we need to find a basis for the row space of A. We apply the Gauss elimination. We transform A into B like that. And here already B has two non-zero rows, that is W1, W2, and because of that, the basis of span by V1, V2, Vc is a basis for row space of A, and it is a V1, V2. And here we get that. The reason is here. Now I change into the column space. I change into the column space. How we can find a basis for the column space? We take back the example in previous. We take the matrix A in the previous examples number 2. A to be the big matrix like that, and you are required to find the column space, the basis for column space of A. And the first method is very simple. You take, because you know that you can take the transpose, then column will becomes rows, and now you need to find a basis for row space of A transpose. And again, applying the Gaussian elimination, you transform A transpose into B, and B now is already in the row echelon form. It has 3 non-zero rows, the first, second, and the third row, and those vector will be basis for column space of A, or the row space of A transpose. Here, column space of A equal row space of A transpose. So you get that basis for column space of A equals W1, W2 up to W3. It is here. However, you should know that this basis is not a subset of column C1, C2, C3, C4 of the matrix A. Matrix A has 5 columns, but that basis is not a subset here, means it is not the vector we can take from here. Chúng ta tìm được một cơ sở cho không gian các cột của A, nhưng cái cơ sở này không phải là vector lấy ra từ trong 5 cái vector, từ trong 4 cái vector cột của A. Nó là cái mà chúng ta xây dựng nên. Vậy chúng ta sẽ cố gắng tìm cách khác. Second method, we keep A like that. We did not do the transpose. And then we apply the Gaussian elimination. We change A into B like that one. It is already in row echelon form. Now we take a look at, we denoted the column of the first one by C1, C2, C3, C4. And the column here denoted by V1, V2, V3, V4. And we look at the columns containing the leading one, that one, and the last column. The first, the second, and the fourth column. They will make a basis for column space of B. They make a basis for column space of B. And because of that, the corresponding column in A, means C1, C2, and C4, will be a basis for column space of A. That is a way we can find basis for column space of A. And that is already a subset of C1, C2, C3, C4. And finally, we can write the third columns as a linear combination of the first column and the second column. Cách làm này cho chúng ta một cái cơ sở. Cái cơ sở này chính là trích ra từ 4 cái cột ở đây. Chúng ta sẽ có C1, C2, C4 là lập thành cơ sở, và nó trích ra từ cái bộ 4 cái cột của ma trận A. Và chúng ta rất dễ kiểm tra cái cột còn lại là một tổ hợp tuyến tính của các cái cột này. It is written in the model here. Next, we need to study the solution of homogeneous system. So, okay. In the first examples, we consider already the row space and the column space. Now we are going to study the known space of A. The known space is what you are seeing on the screen. Suppose that A is an m by n matrix, and we consider the homogeneous system of linear equation AX equals 0. AX equals 0 like that. Then the set of all solution of that one is a subspace of Rn. And that subspace has name known space of A. Here. It is exactly what we defined at the beginning of today. Now how you can see it? It is written in the Moodle. In the slide I up on the Moodle. You can read it by yourself. Once again, I repeat to you. You need to show that one is a subspace. You need to verify the property number 1 and property number 6, nothing more. And it is verified here. So I leave it for you to read by yourself. Now, once again, I say the known space of A is also called the solution space of the system AX equals 0. AX equals 0 is obviously a homogeneous system of linear equation. And here is some example. Suppose that you are given a matrix A like that, and you need to find the known space of A. Means you need to write down all the solution for the system of equation AX equals 0. How you can do it? Here, AX equals 0. You need to find all the solution of AX equals 0, and you need to write it in the form of a vector space. Here it is. You can write it as follows: A to be Z1. And now we apply the Gauss-Jordan elimination. You get that? You get that? Now you get that one. It is already in the row echelon form. Now I call your attention to the column containing the leading one. It is here. The first column and the third column containing the leading one. The leading one is here. The leading one is there. We have only two columns containing the leading one. Means other columns does not containing the leading one. And as I told you, the columns which does not containing the leading one will correspond to the variable we call the free variable. What is a free? Free variable means we can give it any value. And now we give x2 the value s and x4 the value t. That is any number. So whenever you give it the value s and t, you can solve the system according to s and t, and you get x3 equal minus t and x1 equal minus 2s minus 3t. So whenever we have that solution, you can write it as follows. X, now the solution is x1, x2, x3, x4, and x1 to be that, x2 to be that one, and x3 to be that one. X4 is here. Then we write it very easy to know how to write it. S time of this vector plus t time of that vector. Or we can write it equal S v1 plus t v2. Then we can say known space of A to be that, or you can say that it is spanned by V1 and V2. That is a subspace spanned by vector V1 and vector V2. That is the way you can find the solution set, or the way you can find the null space of a matrix A. The next column, the next observation claim that for the same, for one matrix, for one matrix, for one matrix A, the row space and column space always have equal dimension. If A is m by n matrix, then the row space and the column space of A always have the same dimension. Means we can write it here. The dimension of row space and the dimension of column space are the same. Because of that, we can define the rank of a matrix A. The dimension of the row space or the dimension of the column space will be called the rank of A. And we denote it by here. So the notation and the name is nothing as the same. Yeah. Or by formula, you see, the rank of A equals the dimension of row space of A or dimension of column space of A, like that. The next one we did, because we call the dimension of row space and column space by the name, the rank. So we need to define the dimension of the null space. The null space of A has name nullity of A, and we denote it like here. The nullity of A equals the dimension of the null space of A. And of course, the rank of A transform equals the rank of A, like that. And here there's some explanation for you. So I think that we should have a short break now, and then we go back in. So please have a 5 minutes break now.
Or Professor.
Yeah. So let's continue our class. Are you ready?
Yes.
Yes, Professor.
Okay.
Yes.
Okay. So I just repeat just a little part of what I studied before the break. Before the break, we consider column space and row space, and we know that there is one claim saying that if A is any m by n matrix, then the row space and the column space of A always have the same dimension. That is the dimension of row space of A equals dimension of column space of A. And because of that, we are define the rank of A. The rank of a matrix A denoted like that, rank A here. That is the dimension of row space of A, or the dimension of column space of A. And obviously, you will have kind of exercise to find the dimension, the rank of a matrix A, and now you know how to find it. And now I summarize by definition the rank of A to be the dimension of ASA or the dimension of CSA. And for the known space of A, if we consider the dimension of known space of A, we have the notion, we call it the nullity of A, like that. And of course, because we know that we can, when we can change, we take the transpose, rows became column, column became row. So obviously the rank of A transpose equals the rank of A. It is here. It is explained by just only one line in the slide. Now the dimension of solution space means the nullity. Suppose that A is M by N matrix, and suppose that we know already that A has a rank A, small a. Then the dimension of the solution of Ax equals 0 will be N minus A. And that is because you know that the solution space is exactly the known space of A. So the dimension of solution space is what we call the nullity of A. So that observation claim the nullity of A equal N minus A here. And it means that if we take nullity of A plus the rank of A, we always get the number N, that is the number of columns of A. We have that one. I will not explain to you about that property. You can read it in the textbook and you can read it in the slide. I have two things to explain to you, because as I told you from the beginning of the course, that is when you that is solving a system of linear equation is very fundamental skill, and in order to do it by using Gauss or Gauss-Jordan elimination, you always list to the notion of the leading one. And here I explain to you what is the rank of A. The rank of A is a number of leading variable, means that is a number of columns containing the leading one, or that is a number of non-zero rows in row echelon form of A. That is the rank of A. And the second one, the nullity of A, that is a number of free variable in the solution of A x equals 0. Means the nullity of A is exactly the number of column which does not contain the leading one. That is what I would like to tell you. And if you take a look in the Vietnamese textbook, as I told you, the rank of A, or it can be described like a property. The rank of A equals the number of non-zero rows in the row echelon form of A. I can explain it for you in Vietnamese. Trong sách giáo khoa bằng tiếng Việt, đôi khi người ta định nghĩa hoặc người ta giải thích là hạng của một ma trận bằng số các hàng khác không trong một cái dạng bậc thang của ma trận A. Các bạn có thể tìm đọc. I will not use that in here in our course, but here is a one observation. Now, suppose that A is an M by N matrix, and suppose that A has a rank A. Then we have four fundamental subspace, and Together with that, we have 4 dimension. The 4 dimension is given as follows. On the right hand side, we have a 4 fundamental subspace: row space, column space, null space, and left null space. And the dimension of row space and column space is A. Is exactly the rank of A. That is by definition. And then the null space of A, it has a dimension n minus A. We see it on the previous slide. And also, the left null space, it has a dimension m minus A. So from null space to the left null space, there is only one chain. That is, we change from n into m. Because when we take transpose, the number of column of A transpose is exactly m. That is the number of rows of A. That is one thing change here. And so very easy for you to remember. Or I can say it is not so difficult to remember the dimension of those fundamental subspaces. Now here's some examples. You can use the relation between the rank and the nullity of a matrix. Suppose that we are given a matrix A like that, and we denote 5 columns of A by A1, A2, A3, A4, and A5, like that. You have many exercise or many duty. The first one, you need to find the rank and the nullity of A. The second one, you need to find a subset. You need to find a basis for column space of A. But it requires that the basis must be from here, must be one of sum of vector inside A1, A2, A3, A4, A5. And one more thing, if possible, please you can write the columns, the sub-columns of A as a linear combination of the first 2 columns, the first one and second one. Of course, you know how to do it. To find the rank and the nullity of A, you can do as follows. You apply Gauss-Jordan elimination to transform A into B. Now B is already in the row echelon form, like that. Even it is reduced row echelon form. And I denoted the first 5 columns of A by here. And the column of B will be denoted by B1, B2 up to B5. Now for B, it has 3 non-zero rows. It has 3 non-zero rows. So the rank of A to be 3. That is the number of non-zero rows in B. And because A has 5 columns, so we have the nullity equal n minus rank of A equals 3. 5 minus 3 equals 2. So we finish the first question. The second question, you need to find a basis. You need to find a basis for column space of A. And those vectors in the basis must be inside A1, A2, A3, A4, A5. So we look at here. We look at the columns containing the leading one. We have the first column, the second column, and the fourth column. We have 3 columns containing the leading one, and they are basis for column space of B. B1, B2, B4 are basis for column space of B. B1, B2, B4 is a basis for column space of B. And because of that, the corresponding columns A1, A2, A4 will be a basis for column space of A. So that is the second test. And A1, A2, A4 is here. And finally, the last one that I leave it for you as an exercise, and you know how to do it, to write something as a linear combination of something else. That is solving a system of linear equation. Very easy to do. So I leave it for you. Now in next we go to solve a system of linear equation. I mean, we consider any system of linear equation. In previous slide, I show you how to solve a homogeneous system of linear equation. We know how to find it. We apply Gauss-Jordan elimination to change it into row echelon form. Then we decide which one is the free variable. For free variable, we give it any value s and t or something. And then we solve the other variable according to the free variable. And that is the way we solve a homogeneous system of linear equation. But now we consider any system of linear equation. I call it a non-homogeneous system of linear equation. You can look at something like here. Ax equal b. And b is not necessary on 0. B can be any column vector. How you can do it? How you can find on the solution for that? And that claim will tell you how to do it. Suppose that by some way you can guess xp to be a particular solution for the system here. Bằng cách nào đấy các bạn có thể đoán ra được một cái nghiệm riêng, ta ký hiệu là xp của một cái hệ phương trình như thế này. So by some way you can guess xp to be a particular solution. Then any other solution of the system will be written in the form x equal xp plus xh. xp is here. So what is xh? xh is a solution of the homogeneous system of equation ax equals 0. And that we know already how to solve it. Then we can know how to find on the xh. So we need only to guess only one particular solution. And then we add it to xh and we get on as a solution. That is a way to solve a non-homogeneous system of linear equation. In Vietnamese, I can explain to you as follows. Nếu cần giải một hệ phương trình không phải là thuần nhất, chúng ta sẽ làm như sau. Đầu tiên là chúng ta đoán một cái nghiệm riêng xp nào đấy. Việc thứ hai là chúng ta giải một cái hệ phương trình thuần nhất ax bằng 0 để tìm ra một cái nghiệm tổng quát là xh. Cái đấy chúng ta đã làm xong rồi. Và sau khi có cái đấy thì bất kỳ một nghiệm nào khác của cái hệ phương trình ax bằng b nó sẽ bằng cái nghiệm riêng cộng với nghiệm tổng quát. Không còn cái nghiệm nào khác hơn. Chúng ta chỉ có một loại nghiệm đấy thôi. That is the way to solve a non-homogeneous system of linear equation. And it is explained here, so you can read it by yourself. And here is some example. Suppose that you are given a system of linear equation like that, and because right hand side is not on 0, so that one is a non-homogeneous system. Now, how you can solve it? Obviously, we can apply the Gauss-Jordan elimination to solve it. We write it here. Here is augmented matrix. That column is the right-hand side column. We write it here. We apply the Gauss-Jordan elimination to transform it into that one. Then you see, we have the first column and the second column containing the leading one. So the third and the fourth column does not contain the leading one, means the third and the fourth variable will be free. Free means we can give it any value. Now I give x3 the value s and x4 the value t. And we continue to solve the system. We get solution like that. Sorry, let me see. The third is s and the fourth is a t. So here is s and here is a t. x3 is s and x4 is t. And x2 is like that and x1 to be like that. So we can write it as s time of that vector plus t time of that vector plus the last one here. So you see, the last one here is what we call the what we call the particular solution of the system. Or we can write it in this form: s time of u1 plus t time of u2 plus xp. Xp to be that one. Xp to be that is a particular solution for that one. And xh now equal s time of u1 plus t time of u2. It is exactly a solution for the system ax equal 0, the homogeneous system of linear equation ax equal 0. So that is the way we solve the system. The next, we consider that a system, the solution for a system of linear equation. Now, suppose that we are given a system of linear equation like ax equal b, and we need to know if the system is consistent or not. The system is consistent means it has at least one solution. And it is, we have the claim say that the system of linear equation ax equal b is consistent if and only if b lies in the column space of A. Why that? Here is some explanation. Suppose that A to be that one, X to be that column, and B to be that column. Then our equation will be AX equal B. Now we multiply A and X, we get, if we multiply A by X, we write it here. When we realize the matrix multiplication, we get that one. And now we rewrite it in the following way. That matrix is exactly x1 time of a1, a11, a21 up to a, and plus x2 of the, and that one is the second column of A, and plus xn time of the n columns of A, or it is exactly x1 a1 plus x2 a2 plus xn an, and the equation saying that b equal ax means b equal z1. But however, z1 is a linear combination of column vector of A. It means that b lies in the column space of A. So we can see that ax equal b is consistent if and only if b is a linear combination of column of A, or b lies in the column space of A. So that is what we need to explain. There is one more thing. Usually in solving a system of linear equation, you write down the coefficient matrix A, and then you can write one more matrix, we call it augmented matrix matrix bổ sung. So augmented matrix obtained by you write on the right hand side of A the column B, like what you are seeing on the screen here. So then you will see if A, B, if the augmented matrix and the matrix A has the same rank, then the system AX equal B is consistent, is always. Here is some example for you to see. That is an example about the consistency of a system of linear equation. Suppose that you are given a system like that one. It is a non-homogeneous system. Then you are required to see if the system is consistent or not. You can do as follows. You write down the matrix A like that. You apply the Gauss-Jordan elimination. You change it into that one. Then, because of that, you will see the rank of A. The rank of A equals the number of non-zero row of that thing. And that have two non-zero rows. So the rank of A equal 2. We continue. If we consider the augmented matrix A, B like that, then again apply the Gaussian elimination, we get that one. Again, that one has two non-zero rows, means A, B augmented matrix also has the rank 2. And because of that, we know already that the system is consistent. Or we can write it here. V, by that, it's very easy for you to write V equals C times W1 minus 4 times of W2. And because of that, the vector, the column B here equals C times of the first column minus 4 times of second column. It means that B belongs to the column space of A. B is inside the column space of A. Means the system is consistent. That's it. Or you can check, as I told you from the beginning, the rank of A equal 2 and the rank of A augmented is also 2, so they have the same rank. So finally, I summarize some things. Before this slide, we consider 4 fundamental subspace of a matrix. That is for some matrix of any size m by n. Now I consider only special case, that is for square matrix. We suppose that A is a square matrix of size n by n. Then we give you the following claim which are equivalent to each other. Các khẳng định sau là tương đương với nhau. Just only in the case A is square matrix. The first one says that the first claim says that A is invertible. The second claim says that AX equal B, that system of linear equation has unique solution for any column matrix B. The third claim saying that AX equal 0 has only trivial solution. The fourth claim says that the rank of A equal n. The number 5 claim says that n rows vectors of A are linearly independent. And the number 6, the claim number 6 saying that n columns of vectors of A are linearly independent. So now we have 6 claims, 6 equivalent claims. 6 cái khẳng định như trên là tương đương với nhau. And just before your class, some of my students remind me that we have one more claim equivalent to those 6 claims. That is, A has non-zero determinant, because we know already that A is irreducible if and only if determinant of A is non-zero. And so before the class today, we already have the notion, we have already serial equivalent claim. Today we add more claim concerning the rank of A, the rows of A with linearly independent. And I would like to tend to explain to you only one thing, that is why we have a number 4. We know that A is irreducible if and only if AX equals 0 has only deviant solution. It has only deviant solution means the solution set consisting of only one vector. Then the solution set is a what we call solution space. Solution space has only one vector, means it has dimension 0. And the solution space has dimension 0 means nullity is 0. Nullity is 0, then we have the rank of A equal n, because equal the number of the column of the vector A, of the matrix A. That is what we studied already in serial slide before. So now I summarize some claim, some equivalent claim here. And because I am a little busy today, so today I stop our class a little earlier than usual. If you have some question, please ask me right now, or you can send me an email to ask about that. So please.
Professor, when will you put the slide on the Moodle?
That
slide, this slide for today's lesson.
It is on already in on the Moodle.
I can't find it.
That is
the scroll to the very bottom.
I only see lesson 4. I mean lecture 4 slides.
It is lecture 4.
That is the lecture 4. That is the lecture 4. We have not yet finished the lecture 4 because it is.
So do we have our assignment today?